Hey, this is Dr. B, and let's take a look at net ionic equations. These, in the purest sense, are what really happens in a chemical reaction. Let's have a look at an example. Consider the reaction of copper 2 chloride, which is dissolved, with sodium hydroxide, also dissolved. It should form, as you probably know by now, copper 2 hydroxide and sodium chloride. And we can balance it. Fine. But let's think about what's actually occurring. Let's write what's known as the Ionic Equation, meaning since it's dissolved, let's write what's really in the flask, which is these ions, these ions, these ions, these ions, but not these ions. Note that it's a solid, so this substance exists together, but we also have some sodium ions and some chloride ions. And when you write that all out, and it's a lot, you should see that there's a lot of things here that aren't reacting, right? Copper 2 plus, yes, I don't see it on the product side. Chloride, no, it's on the reactants on the product side as well, so it cancels out. We call those spectator ions. Cancel all of the spectator ions out, and that should give you an idea of what's actually reacting. And in fact, the only thing that's reacting are the copper ions with the hydroxide ions. Water is a solvent, it shows up as both sides, and that's it. Take-home message: in most cases, if you're going to write the net ionic equation, just write the ions that form the precipitate. You might want to make a note of that. We call this the net ionic equation. It is, in the purest sense, what really happened, but let's point out some limitations. This is not enough information for somebody to do this chemical reaction. They'd say copper 2 plus what? It doesn't exist in the stockroom. It's just the ions. It always has some counter ions to go with it. It does tell you that it doesn't matter so much what those counter ions are. I mean, they will affect things like the rate of the reaction, things like that. But if you got some copper 2 plus anything, plus some hydroxide, lithium hydroxide, sodium hydroxide, you'll make this stuff. Fine. So this is what really happened. It is misleading because the ions are always paired, but that's a nice pure look at a chemical reaction. Now, noting that we just really want to focus on the precipitate, let's do some more. It should get much easier. Let's write the net ionic equation for the reaction of potassium phosphate and calcium nitrate. Now, they did note that nitrates are always soluble, as well as group 1 ions are, so that should help us. Potassium's a group 1 ion, so that's not going to be the precipitate. And the nitrate containing product will not be the precipitate. So what's going to be the precipitate? Potassium nitrate is going to be one of the products. The other one will be calcium phosphate. This has to be our precipitate. It doesn't have the group 1 ion. It doesn't have the nitrate. So that is your big focus. All you have to do to write the net ionic equation is say, hey, 3 calcium ions combined with 2 phosphate ions, and you've got yourself a net ionic equation. We balance it out, but we don't really have to if all we're doing is focusing on this. And we find that there it is. The calcium ions and the phosphate ions combine to form the precipitate. Try to always remember that although this might seem a little strange, it truly is what actually happens in the chemical reaction, and I hope that example helped. Let's do another. We're reacting sodium hydroxide. Well, that's a group 1 ion there. That thing will not be the precipitate. Magnesium nitrate, so I guess the precipitate's going to be the magnesium hydroxide. Fine, that's our focus. So magnesium ions, balancing it just to be good. Magnesium ions react with the hydroxide ions to make magnesium hydroxide. So the really useful shortcut that only shows up fleetingly there is focus on the precipitate. This could get you in a little bit of trouble later on when we do things like weak acids and bases, but this is a good place to start. This is an introduction to net ionic equations.